So welcome everyone to our global NCG seminar America site today. So our speaker is my friend Zhizhang Xie from Texas A&M University. So Zhizhang will tell us his recent work on Gromov's dihedral extremality and the rigidity conjectures. So please, Zhizhang.
Okay, thank you very much to the organizers for the invitation, and thanks to Sean for the introduction. So I will basically report on our recent result on the solution to Gromov's dihedral extremality and rigidity conjectures. This is joint work with Jingming and Guoliang. So let's just get started. So let me briefly describe what the conjectures. There were two conjectures. Of course, they are set up in the same setting. So here's Gromov's dihedral extremal conjecture for convex polyhedron. And later on, I will introduce a more general statement. But for now, let's just focus on convex polyhedron in Rn. The usual, you think of a convex polyhedron in the usual way, flat boundary, flat and have corners and so on and so forth. And then the conjecture of Gromov is about, suppose you have another metric on the same space, such that you will have three comparison. First is the scalar curvature comparison, that the new metric, the scalar curvature, is greater than or equal to the scalar curvature of the flat one, which is 0. And then you have the mean curvature comparison. Mean curvature means how the boundary is curved relative to the domain. So, and you have the mean curvature of the new metric on each face is greater than or equal to the mean curvature of the original metric, which is supposed to be flat. So it's again mean curvature 0. And now then the third one is the dihedral angle comparison, which says the dihedral angles of the new of the faces where they meet of the new metric is supposed to be less than or equal to the dihedral angle of the original metric. Now, if you think about dihedral angles, you can think about dihedral angles as a notion, the replacement of mean curvature in a distributional sense. Well, to be more precise, it should be probably pi minus the dihedral angle would be the mean curvature. So this is in line with the second condition, that the mean curvature of the new metric is greater than or equal to the mean curvature of the original one. Now, with this setup, then the conclusion is then everything have to be the same, actually. The scalar curvature have to be the same as the original one. The mean curvature has to be the same as the original metric. And then the dihedral angles everywhere. Oh, by the way, for the new metric, the dihedral angles actually is a function. It doesn't, even when the two faces meet, the dihedral angles can vary. Okay, it's not assumed to be constant along where two faces meet. But anyway, the conclusion is they have to be the same as the original one, which is actually a constant for the convex polyhedron along each edge, let's say. So that's the dihedral extremal. So in other sense, the flat metric, the original flat metric on this convex polyhedron is extremal in this sense. In other words, intuitively speaking, this is saying you cannot change the metric on this convex polyhedron in such a way that you increase scalar curvature, increase mean curvature, and decrease dihedral at the same time. That's just that's impossible. And then I will motivate I'll explain a little bit where these conjectures come from. But for now, let's just say let me again move ahead with the dihedral rigidity conjecture, which says basically the same setup again, and then the conclusion is actually the new metric has to be flat as well. Okay, so So this is about, so this is saying the original metric on this convex polyhedron, the flat metric, is rigid in the sense that if you have these conditions, then there's only one metric that can, well, in some sense, there's only one metric can realize these conditions. Okay, so let's motivate these conjectures. I think Gromov, of course, explained, in his in recent years, he had these many papers or lecture notes explaining various conjectures, and these two conjectures are two of a long list of conjectures proposed by Gromov. So one of the, I believe one of the motivations for these conjectures come from, in the two-dimensional case, from the Gauss-Bonnet theorem. But of course, I think Gromov also draws motivation from, in terms of comparison theorem in Riemannian geometry, there are many of those, in terms of Ricci curvature or in terms of sectional curvature comparison theorem like those. And now, there's partly, of course, is a motivation from that as well. But on the other hand, we do know, sectional curvature, Ricci curvature is a much stronger notion of curvature than the scalar curvature. So it is still amazing to actually, when you use scalar curvature, you can still have some comparison theorems like this. This is already very, very, amazing to have a phenomenon like this. But let me explain a little bit from the point of view of Gauss-Bonnet where these two conjectures sit. So we all know the Gauss-Bonnet theorem, which says if you have an oriented two-dimensional surface with piecewise smooth boundary, which means it's just like our polyhedron, it can have corners, that's okay. Then the Gauss-Bonnet theorem says this is the Euler characteristic of X, and 2 pi is just a normalizing factor to put there to make this formula equal to the right-hand side. So this is the integration of the Gaussian curvature over the surface. And we know that in a two-dimensional case, the notion of scalar curvature or Ricci curvature or sectional curvature is all the same up to some fixed constant. So might as well just think of this as a scalar curvature up to some renormalization. This is usually when we talk about two-dimensional objects, CI is the boundary, the curves, the piecewise smooth. So you have different components of the boundary. And then this is usually called the geodesic curvature, but this is put in the context of what we call the mean curvature in the conjecture. These are just the mean curvature of the curves sitting inside this surface. And where these are exactly the so-called signed exterior angle is, let me draw a picture here. It's just, maybe, sorry, this is maybe not a very good picture. So let me redo this. So it just means the tangent vector of this curve and where it meets the other curve, and then the two tangent vector of these two curves, there's a turning angle. And this turning angle has a sign, depends on whether this orientation is compatible with the orientation of the assigned orientation on X, or is the opposite, then you have a sign. In any case, so since the conjecture of Gromov we were stated in terms of dihedral angles, so let's just rewrite the Gauss-Bonnet theorem in terms of dihedral angles. Here, the dihedral angle of this guy right here is by definition equal to pi minus the signed exterior angle. So dihedral angle is between 0 and 2 pi. Now, if we just rewrite it, just just a trivial rewriting of this. Then here, of course, there's pi times the number of vertices. But other than this term, this is exactly what the three geometric quantities that appeared in the comparison conjecture we just stated: scalar curvature, mean curvature, and then dihedral angles. Now, I hope it's already obvious to see that the Gromov's conjecture in the two-dimensional case is exactly Gauss-Bonnet. Okay. So yeah, because you cannot increase these two terms and then decrease this term, but because the Euler on the left hand side, this quantity is fixed on the same x. Okay. So that's where the motivation, at least one of the motivations, for these two conjectures of Gromov. So here's so what we did is indeed these two conjectures are true. Here's the theorem. We just say when P is a convex polyhedron in Rn, then when these three comparison conditions on scalar curvature, mean curvature, and dihedral angles are satisfied, then yes, the scalar curvature, it has to be equality instead of inequality. But this is for the extremal part. But for the rigidity part, we prove instead of G is flat, we actually show we only show it's Ricci flat. Okay, this is because of the method, okay, we use. So currently we don't have flat, but we've implied that G is Ricci flat. Of course, in dimension 3, Ricci flat and flat are the same. So in dimension 3, we do solve Gromov's dihedral rigidity conjecture completely. Okay. So let's see. Let me maybe just a little bit history where what has been done before our result. Well, that's quite many years ago. Gromov showed that this dihedral extremal conjecture holds for a special class of convex polyhedron with some extra restrictions on dihedral angles. For example, the standard Euclidean cube, where the way Gromov proved this is by saying if you have a convex polyhedron that satisfies where the angle condition sets on symmetry, for example, this guy, you can do reflections of this guy to make it, roughly speaking, if this guy has some symmetry built in, then you can use the original convex polyhedron and do reflection to get a closed object or a complete object. And then in that setting, one can then apply index theorem from on a closed manifold on a complete manifold too. So basically, in this case, you reduce to the case of torus in some sense. But of course, as this approach does require some nice symmetries of the polyhedron to start with. Okay. And more recently, in the past couple of years, Chao Li proved the dihedral rigidity conjecture for a special class of convex polyhedron, in particular for the so-called cone type. Cone type means you have some base, and then this polyhedron is a cone over that base. And then it satisfies, sorry, I'm receiving a spam phone call. So it's a cone type 3-dimensional polyhedron that satisfies certain angle conditions. Some extra angle conditions. These extra angle conditions are imposed. It's a technical assumption because of the method, he used a minimal surface method, and this actual angle condition has to be imposed to achieve some regularity of minimal surfaces. Okay. And then also there's a prism type. Which means it's a two-dimensional polyhedron of the base, and then you cross some interval or some cube. But as you have noticed, this approach, because it's using minimal surface, it does have the restriction that besides the actual angle of conditions, that you have to be inside the dimension less than or equal to 7. That's because of the method, again, of the minimal surface method. Okay. Any questions so far? Okay, so let me actually just again talk about why these two conjectures. Well, of course, these conjectures are already very interesting, but are there even some applications of these conjectures? For example, here's one, just to motivate us a little bit further on why these conjectures are interesting. Here's an application of Gromov's either of these conjecture actually. So the positive mass theorem will be a consequence of either Gromov's dihedral extremal conjecture or the rigidity conjecture. Either one would imply the positive mass theorem. Now, of course, positive mass theorem has been proven by Xun Yao and Witten which says the following: if you have a so-called complete asymptotically Euclidean manifold of dimension at least 3, asymptotic Euclidean means this manifold at infinity looks like very close to be a Euclidean space. That's but there's a precise definition, of course, but I will not get into that. And the assumption here, the key assumption here is its scalar curvature is non-negative everywhere. Then the conclusion is there's the ADM mass of each end, so it can have more than 2 ends, so more than 1 end, but on the ADM mass on each end has to be non-negative. Now, this term I will not define today, but roughly speaking, this term can be interpreted as some integral of the mean curvature. If you take a very large sphere at infinity and look at the mean curvature of that sphere, integrate over that sphere, and you let this sphere go to infinity, you calculate this quantity, the limit of this quantity at infinity. This is roughly what this ADMS means. So it's some, yeah, okay, but it has a real physical meaning. So that's the positive mass theorem in dimension less than or equal to 7. This was proven by Xun Yao without assuming X to be spin. But if you assume X is spin, then Witten has a method, a Dirac method. This is a proven, yeah, Xun Yao's method is minimal surface method, and then Witten's method is Dirac method. So then it does require X to be spin, but then it works for any dimension. So this is a common theme, I think, in this sort of business on scalar curvature. You have these two methods. One is minimal surface, one is Dirac method, and one has the advantage that you don't need to assume X to be spin. And the other has the advantage that there's no dimension restriction. Okay. I will explain a little bit how you would go from this to this theorem. Strictly speaking, it's not exactly the two conjectures of Gromov I've stated that would imply this per se. I would need a slightly more general version of Gromov's conjecture, not just the manifold itself, putting a new metric. Actually, I would say you have the target manifold, which is convex polyhedron itself. I would look at another domain manifold, which could be different from the target. but you have some degree non-zero map, map to the target, and then there's some comparison with respect to this map or these quantities, and then you still have extremality or rigidity for that general context. Then from that general result, that slightly more general conjecture, you would get positive mass as a consequence. So in that sense, this maybe slightly general version of Gromov's dihedral extremal or rigidity conjecture, you can view it as a localization of the positive mass theorem, because the positive mass theorem in some sense happens at infinity. At least the consequence, this mass happens at infinity, but somehow the Gromov's conjecture is about some compact region, which is more localized. But of course, how this localization is related to things at infinity is precisely this assumption that the scalar curvature is assumed to be non-negative everywhere. Okay, so here's a more general comparison theorem. Now, as you can see, the theorem, the conditions won't fit in one page, so it is a bit long. But let me explain that all the conditions are actually fairly natural. But it is true. The statement of the theorem actually covers 2 pages. Okay. So now this is the more general version of the comparison theorem I just mentioned just 30 seconds ago. Is instead of talking about one fixed manifold with picking a new match, comparing 2 different metrics, you say you have a target manifold and you have a domain, and then they are compact oriented Riemannian manifolds. Now with corners, well, we're dealing with like polyhedron, so we allow corners, of course. The corners is where the dihedral angles appear, of course. So the first 2 assumptions is that the curvature operator of G is non-negative. So all these 3 conditions are on the target. It's like our convex polyhedron that on all the geometric quantities in some sense are assumed on the target. When we want to say the target is rigid or extremal in this comparison context. So first, the curvature operator of G is non-negative. This is like saying, for the convex polyhedron, our curvature operator in there is basically 0, but you allow it to be greater than or equal to 0 in the general context. And then for each codimension 1 phase, M is supposed to be convex in a sense that the second fundamental form is on each phase of M is assumed to be non-negative. This is like our convex polyhedron. Each phase is actually flat, which means in that case, the second fundamental form is constant 0, but here we allow to be greater than or equal to 0. Now here's a assumption that the dihedral angles for all the dihedral angles doesn't have to be constant, but they're always less than or equal to pi. So in other words, this is also in line with the second condition that M is supposed to be somehow mean convex. So convex, just convex, not mean convex. I mean convex. Okay. So we do now, as I guess you probably have guessed, the method we're going to use is the Dirac method. So at some point, the spin condition would appear naturally. So of course, in the Gromov's original conjecture, we're just looking at the polyhedron, so which of course is spin, so nothing to worry about. But here in the general context, we would work with a manifold M and N. There's a map, which is a spin map. So this is slightly more general than, or you say weaker than the fact that M is spin and N is spin. So we don't have to assume M individually, M and N to be spin. It's just together, they give you a spin structure. So in other words, this basically condition, I will explain this in more detail. Basically, the spin map means if M, it turns out to be spin, then this condition means N has to be spin as well. But it's weaker than that. So I'll get to that. I'll give the details just in the next, or maybe next, the slide after. And also there's a technical assumption is this map is a corner map. Corner map, it just means it should respect the corner structures of N and M. Okay, you should not have some crazy degeneracy of these corner structures. Okay. Now, with these two conditions, and then here comes the natural comparison. These are probably not surprising. You have the scalar curvature comparison, mean curvature comparison, dihedral angle comparison. Now, you also have this condition right here that F is supposed to be area non-decreasing. So, area non-increasing. So area is shrinking. So area shrinking, and on the boundary, its distance shrinking. So that's the assumption. Now you would wonder, in the original conjecture of Gromov, there's no such assumption, because we didn't really compare G, the new metric, with original metric by saying it has to be area larger or smaller or distance. But then you think about the flat case, because the flat metric on the polyhedron, you can always shrink it, rescale it. By rescaling the metric of the flat metric, it's not going to change the scalar curvature. And because the face are flat, you're not going to change the mean curvature. The dihedral angles, of course, are remains the same under rescaling. So by trivial rescaling, you will see that this condition will be automatically satisfied in that context. So for Gromov's conjecture, at least for convex polyhedrons, then this is automatic. Okay. So and here comes next, these two conditions. Of course, again, this is say the target should have non-zero Euler characteristic, and then the last condition is that there is an a hat degree. The a hat degree makes sense because we have this spin condition. So the a hat degree is supposed to be non-zero. Now, again, in a Gromov original conjecture, these two conditions are automatic because we are dealing with a convex polyhedron. The Euler characteristic will be 1, and then this map is essentially a diffeomorphism. So of course you would have degree 1 in that context. So now you would wonder, in a general context, why do we need these two conditions? Because later on we're going to use Dirac method, and then so the twisted Dirac operator we're going to use, its index is going to be precisely the Euler characteristic of M times the degree of this guy. So assuming these two are non-zero, which means we're going to have a twisted Dirac operator with non-zero index. With non-zero index, you can find a non-trivial, harmonic section, and then that would allow us to do this, prove the theorem. But this is where these two conditions come in. Okay, so now, and then the conclusion is, yes, with this setup, and then the scalar curvature has to be the same, mean curvature have to be the same, dihedral angle has to be the same. Now, if we assume actually a little bit further, so this is just extremal part, and here comes the rigidity part. So it turns out if you assume the target, so this condition, of course, does not apply of the Gromov's original conjecture for convex polyhedron, because our original metric would be flat, it's not Ricci positive. But for the moment, for example, this part will become interesting if we work on a part of a region of a sphere, let's say. If you're looking at spherical polyhedron, then this will be very much relevant. So this saying, if the Ricci curvature is positive and the F is assumed to be distance decreasing on the entire N. Originally, remember, we only assume to be distance non-decreasing on the boundary. So if you assume slightly stronger that its distance decreasing on the whole thing, then F has to be a Riemannian submersion. Especially when the dimensions are the same, then this has to be a Riemannian isometry. And then if you don't like this distance decreasing on the whole thing, this, you just want to stick with the area area non-increasing in the interior, then with this slightly modified assumption, you can also again get the rigidity. So it's a submersion, and then if the dimensions are the same, then it has to be a Riemannian isometry. So that's corresponding to the rigidity part, because you prove isometry. That's the two metrics essentially are the same. Now, in the case that this is flat, then we show that the top domain has to be Ricci flat, and this is where for the original Gromov conjecture, this is why we also get Ricci flat instead of flat. And consequently, of course, in dimension 3, you show that the domain is also flat in this case. Okay. So I hope I've explained the statement. I made clear of what this theorem, this more general theorem, is about. So with this, let me just briefly comment on how you get from this slightly more general, this more general version of a comparison theorem of this positive mass theorem by a result of Lockham, which says if you basically prove this by contradiction. By a theorem of Lockham, it says if you can reduce the result to basically a complete asymptotic Euclidean manifold with one end. Okay, that's you can by some lemma you can reduce it to one end, and now you assume that one end has negative math. Then there's some perturbation of you can modify the metric so that it still is scalar curvature, still non-negative everywhere, and with two extra properties. Now near infinity, it's exactly not just asymptotically Euclidean, you can make it exactly Euclidean. Inside, not only it's scalar curvature non-negative, you can actually make it positive somewhere. So now if you have a manifold that is completely Euclidean outside, and inside scalar curvature non-negative and somewhere positive, then you would cut out this non-trivial region, just throw the Euclidean part at infinity away. Now you compare this to exactly the Euclidean ball or some Euclidean cube, whichever way you prefer, then we are exactly in the context of this comparison theorem, because then you would have scalar curvature, mean curvature, dihedral angle, depends which boundary you cut, okay? And then they satisfy all these conditions. So it would imply that the scalar curvature has to be the same as the scalar curvature of the flat metric. Well, that's a contradiction, because we just, by Locham's result, we just constructed a metric that is positive, with scalar curvature is positive somewhere. So that's a contradiction, and that implies the positive math. But of course, for us, so in that sense, so this theorem implies the positive math theorem in a spin case. Of course, that's the original result written. So in that sense, in this context, this theorem can be sort of as a localization of the positive mass theorem in a spin case. Okay. I hope that makes sense. Now, let me briefly comment on some history of this type of comparison results. For closed manifolds, and that means there's no boundary, of course, no dihedral angle. Then this theorem here for closed manifolds, that's a result of Goethe and Selmermann. Now, in the case of manifolds with smooth boundary, I should be precise, actually, smooth boundary. This is in a of even dimension. Okay, now, this is because of the method that, for example, if you think about this condition right here, if you think about closed manifold, for example, you're not going to have a closed manifold of all dimension that has non-zero Euler characteristic. So one natural way to go from even dimension, or from odd dimension to even reduce it to an even dimensional case, you would cross it with the interval, for example. But that would land you in a manifold with corners case. So studying manifold with a corner is not just sort of a technical thing. I mean, it does bring in it's important that we actually study manifold with corners. Okay. But anyway, so yeah, for manifold with smooth boundary, which means no dihedral angle, this type of comparison result was a theorem of Lot. So let me okay, I guess that's basically the statement of the theorem and a little bit history. Are there any questions? If no questions, I'm going to move on to outline some of the key ideas that come into the proof of this theorem. First, let me explain that I said, what is a spin map? The spin map just means the bundle of this bundle, not just n itself or the tangent bundle of M is, as I said, it's an assumption that they together form a spin structure. In particular, in this case, together there is a spin bundle over the manifold N of this form. Okay, this is the tangent bundle and this is the spinner. Locally, of course, it makes sense. In order to define this globally, you need the spin map, the spin condition. Okay, so we're going to study the so-called twisted Dirac operator, which means the Dirac operator associated on this bundle here. So for people who are familiar with this sort of, I guess probably everyone in this audience is familiar with these sort of techniques, that in the case that when M and N are exactly the same and N is a spin manifold, if you study this guy right here, this operator is exactly the de Rham operator on the manifold. So in that sense, yes, we are really going back to the Gauss-Bonnet theorem. So the index we're studying is really the Gauss-Bonnet, the Euler characteristics. But of course, when there are different dimensions, there's this extra degree, that a hat degree comes in. But if they're the same dimension, we're literally looking at studying the Euler characteristic. Okay. So in order to prove that there are basically two sort of key ingredients for the proof. One is we should have some result that compare by using, we can use the Dirac operator to deduct the comparison of scalar curvature, mean curvature, and the dihedral angles. So in the manifold with a smooth boundary case, this is the result. This is for closed manifolds that was done by Goethe and Salomon, and then for the manifold with smooth boundary, this was done by Lot, which says by using this Dirac, this just twisted Dirac operator we just defined, for each section of this bundle here, we have the following comparison. You see the nabla. So basically, this is people are familiar with. Basically, you work with the Bachner type argument. You just need to identify all the geometric terms that appear there's some curvature, extra curvature term. We just need to identify what appears exactly in this context of this curvature term, this curvature operator. It turns out we have the scalar curvature coming from the manifold N. That's not surprising. We're dealing with twisted Dirac operator here. And then you have the curvature operator. Oh, I think I'm stating a slightly more general fact here. So you can be even more precise. You don't have to assume F is distance decreasing or area decreasing. Actually, you can put the actual factor here to make it very precise. So in other words, maybe let me just go back. What I'm trying to say here is for this theorem, there's a slight generalization of the theorem. You can put some factors here according to how the F rescales the metric locally. Okay, so there is a slight generalization of this result. But let me just focus on this case. But anyway, so you can basically the Dirac operator detects the comparison of scalar curvature, comparison of the mean curvature, and then you have this boundary term. This is the Dirac operator that you define out of by using the normal vector of the boundary that you would define some boundary Dirac. So this term eventually will go away once we impose a natural boundary condition. So right now it appears because of Stokes theorem, but this will eventually go away because we're going to study the Dirac operator with a boundary condition. So what really comes down to it is this non-negative term here, and then the comparison scalar curvature, comparison of mean curvature. Okay, so what we need for the manifold with corners case is we need to identify exactly, single out again this dihedral angle comparison. So for these terms, it's not surprising. Sorry, the scalar curvature, mean curvature, at least away from the corner, I would say maybe it's not surprising that we also see exactly these terms appearing. But now the delicate part and exactly where actually we need some, we did spend quite a few pages to explain all the details to get exactly the dihedral angle comparison. Now, of course, philosophically speaking, as I said, dihedral angles these two terms are distributional mean curvature. So again, of course, they should appear naturally. But to really get these terms on the nose, we do have to spend some time. Okay. Let me give let me just explain how you actually prove this by draw a picture. So the idea, at least philosophically, is not that difficult, because so you have a corner right here. So instead of dealing with the corner right away, you just approximate this corner by a small curve that's approximating, getting closer and closer to the corner. Now, of course, if you look at these parts, these parts are the just original face. So what you're gonna get will be exactly the mean curvature of the original face. But what about this extra part here? This extra part, the mean curvature, when you curve is shrinking, of course, the curvature will blow up. The mean curvature will blow up like 1/r. But on the other hand, the length of this curve is also shrinking like 1/r. So if you calculate and you take the limit, the leading term is exactly the angle. And that's essentially the proof, okay? For the dihedral angle. And now you would wonder what happens in a higher dimensional case, because you can have a corner that looks like looks like a spherical cone instead of a curve. You would have a sphere, cone over a sphere. But then you realize that the mean curvature of the sphere, again, you have a sphere of higher dimension, when you shrink the sphere, the mean curvature blows up like 1/r, but the area of the sphere decays like greater than r squared. So there's no contribution from the higher dimensional case. And so the only contribution, the actual contribution, would be the dihedral angles. Okay, and that's essentially the proof. But of course, there's some estimates we have to do, but that's in spirit the actual proof. So the next thing, as I said, so we have a proposition that allows us to use the Dirac operator to capture the comparison of scalar curvature, mean curvature comparison, and dihedral angle comparison. The next thing is, now suppose we can show that this Dirac operator, you can find some appropriate self-adjoint extension of this Dirac operator that has Fradon, which is Fradon, and the index is non-zero, right? And then you would have a section phi in the kernel. Then on the right-hand side, it will be 0, and then look at all these other terms. If you go through the assumption of the theorem, all these terms are non-negative, and then you say this term is 0, then you're done, because then everything has to be 0. So the next ingredient what we really need is to find some self-adjoint extension of D that has non-zero index. Okay, so that's the next theorem. So there is, yes, you can put a boundary condition. The boundary condition, this is some local boundary condition that's naturally given by the normal vectors of the faces of these two manifolds. Roughly speaking, in terms of the de Rham operator, in case D, this guy is just a standard de Rham operator. If you put the standard boundary condition, this will be like the absolute or relative boundary condition that we use for de Rham operator. In a sense that the absolute boundary condition means when you look at a form, it does not at the boundary, it does not contain the normal direction. That's the absolute boundary condition. Okay, but in the general context, this it's not much different. You just put that boundary condition there. Now, here comes the essential part, that under the dihedral angle assumption, that the dihedral angles are less than, so all the dihedral angles of M is less than pi, and then we have the comparison that the dihedral angles of N is less than the dihedral angles of corresponding dihedral angles of M. Under this assumption right here, one can show that this operator under this natural boundary condition is essentially self-adjoint. Furthermore, it would be out of the construction, you will see that it's also Fradon. Well, for one thing, for example, you can see that the domain of this guy is essentially self-adjoint, and the domain of this guy is the H1 space. So you will see it's Fradon, okay? And then the index will be exactly the degree of F. A hat degree of times the characteristic, Euler characteristic of M. Okay, so I should, maybe I have a few, let me go ahead. But I do want to point out, here's a remark. So the point is, how do we compute this index? So as I said, the only remaining piece of the puzzle is we need to compute the index. And so to make sure that this index is non-zero, and this is a part of our assumption that this is non-zero. So we just to make sure that the index we get is exactly this. So how do we do this? And of course, index theory on manifold with corners or manifold with singularity is a delicate business. So in order to compute the Fradon index, we would actually deform the manifold with corners to manifold with smooth boundary. Now, of course, in this deformation process, we should make sure that the index does not change. So, but now, probably people would, I mean, it's relatively easy to see that once you are in a manifold with a smooth boundary case, then the index computation is classical. So the key part is, how do you deform the manifold with corners to manifold with smooth boundary while still keeping the index the same? And then here's the essential self-adjointness of this operator comes in. This is a key step in proving the Fradon index remains constant under this deformation. I do want to point out, in a previous version, our paper, we claimed such a homotopy invariance without showing the essential self-adjointness of this D. And this has been corrected in a new version, which appeared this morning, in fact. Okay, so we do have now all the details in the new version that shows the essential self-adjointness of the operator, and also we show with details that how this essential self-adjointness allows us to change the operator or the manifold while keeping the index the same. Okay, so now I also want to point out this dihedral angle condition is sufficient and essentially actually almost necessary for this operator to be essentially self-adjoint. So Chang, how much time do I have? Or should I stop now? I
10
do
minutes.
have a few slides. I can explain roughly the key ideas why this operator is essential, and to show you where the dihedral angles condition come in. But I can stop now if there's a time constraint.
Oh, we started around 2 in Central Time, so you can have until 3.
Okay, 3. Okay, so here's, it's just by a computation. Okay, so how you show this self-adjointness, essentially self-adjointness of the operator, is done by some computation. Of course, in conic metric. Okay, so we have to use some conical metric analysis. This is what we learned from Shiger and other people after him. So let's look at the simplest case. Let's look at the cone, the standard, just some sector. This is in 2-dimensional case. You have the link, which is the arc. You have some angle alpha. Look at the standard de Rham operator on this cone, 2-dimensional cone here. It's a conic metric, but so it turns out this is probably not very surprising. We're going to write everything in terms of cylindrical coordinates, or you prefer polar coordinates. Just write everything in polar coordinates. So then you will need to do a computation. Once you are in polar coordinates, the operator looks like this. Okay, it's some trivial. Okay, I wouldn't say trivial, but some standard identification. So once we're in this, the boundary, if we put the standard boundary condition, like the absolute boundary condition, which means you have a differential form, then on the 2 edge, you should have no d theta at the 2 endpoints on the link. Okay, I'm saying on the link right here, you should have no. So, and then it's a very straightforward computation in calculus that shows that the spectrum of this operator, well, first, this the operator P on the link with this boundary condition is, in a 1-dimensional case, it's easy to show that it's essentially self-adjoint, and then the spectrum is exactly this. And now you see that the angle comes in. Now here's a result in conic metric this analysis that for any type of this operator, if the operator on the link is essentially self-adjoint, then you want to see the operator on the whole thing, whether it's essentially self-adjoint or not. Of course, by von Neumann's theorem, we know it's really just depending on whether the deficiency indices of this operator is 0 or not. And this later condition, do it by a computation, you show that it's the same whether the operator on the link has the spectrum is at least 1/2 or not. It's if and only if. Okay. So now you go back and look at this. When is this spectrum a wave? It's outside of the region -1/2 and 1/2. You will see that alpha has to be exactly. So if and only if alpha is less than pi, equal to pi. Okay. Now okay, maybe I should quickly stop. So now now of course we are not. This is like in a very basic trivial case, but you can imagine, of course, our maps would come in because it's not really the standard de Rham, because it would have some angle rotating. The boundary conditions are not exactly the standard boundary condition. Now you would say when there's some angles alpha compared to beta, then you would do the same type of calculus, just identify, and then you will see the angle, the spectrum turns out to be exactly this term right here, and now some a simple arithmetic would tell us that on the link, the boundary condition is 1/2, at least 1/2, if and only if these two conditions are satisfied. That's precisely, you see that the angle, dihedral angle comparison exactly appears in the essential self-adjointness of the operator. Okay, this is essential. As I said, this is essential. This is if and only if. So roughly speaking, this will, that's what I said. This is almost a necessary condition. Okay, but anyway, now in a higher dimensional case, you would say, what about the higher dimensional case? In a higher dimensional case, higher dimensional, the link is a sphere, so you have positivity. So by this Gallup-Meyer inequality on forms, you will have a lower bound. So that gives you the spectrum gap again in a higher dimensional case. Okay, and that's the end. Thank you.
Thank you. So, any questions or comments?
I just have one stupid question, which is the following, which is that, it could be that your operator is not essentially self-adjoint, but that you could find a good self-adjoint extension if the deficiency indices are equal, and if you had some symmetry around, which would allow you to select the right extension.
Yes. Yeah, exactly. In fact, it turns out in this business, thank you, Alan. Very relevant comment. So in this business, even if it's not essentially self-adjoint, and from this sort of conic metric calculus, you can, as long as the deficient indices are the same, yes, you can have many different self-adjoint extensions, and this self-adjoint is one-to-one corresponding to the symmetries between the two deficiency spaces.
Right.
And indeed, in other situations, it's very possible that if you pick the right extension, you can still have this type of result. But of course, it will be more delicate because then one has to be careful, because when you deform metric, you have to be careful. But it's very possible. This still applies, to a more general context. Yes.
Right.
Mm-hmm.
You said that the theorem is a localization of the positive mass theorem. Is it also some kind of, I don't know, quantification? Can it tell you how much mass there is in a box, that kind of thing?
Yes, in spirit, I'm sure one can. So in that regard, there are some results in that sort of quantitative result already. Well, first by Yao and his collaborators, which means instead of saying, basically quantify how the mass will be controlled by some, instead of the global, maybe more localized, but with some distance assumption, like scalar curvature has to be in certain region larger than certain number, lower bound. But of course, that's all in the spirit of, nowadays what we are doing in terms of finite propagation or some scalar curvature lower bound. Yes, there is. But yes, and also I'm sure one can, even in this regard, if we want, instead of having exactly extremal or rigidity, one can also quantify this theorem by some quantification. And that's definitely, one just needs to sit down and write down the right quantifications, but definitely there's a definite quantification of this theorem and then a quantification of the positive mass as well. Yes. Yes, exactly.
Thank you.
Mm-hmm.
Are there any more questions or comments? Okay, let's thank Zhizhang again for a wonderful talk.